Okay, so as we're talking about different ways to model data, I invited Dr. Souza, João Vitor Souza, to come introduce you to the concept of large language models as a way to start getting into unstructured data in AI. I've asked Dr. Souza to present because he's much smarter than I am on this topic, and he's been studying this deeply and developing research and science in this space. So he's definitely going to be a much better person to talk to you about this than I. But I'm happy to answer questions afterwards or anything like that. Yeah, Dr. Souza is a faculty at Duke as of August. He's an assistant professor of emergency medicine and working under our division, the Division of Translational Health Sciences. And he's my colleague from Brazil. João, they don't know where Brazil is, man.
Oh, no. We got to fix that.
Yeah, we got to fix that. Yes. All right.
João, just before I start, is this class from the master students as well?
Yes, they're all first-year master students in biostats and epidemiology. We have some people visiting as well.
Okay, cool. Nice.
Cool.
All right, folks. Thank you for having me. Thank you, João Ricardo, for the presentation. As he said, I am a part of the Division for Translational Health Sciences and also a researcher at the Gemini Global Emergency Medicine Innovation Implementation Research Center. And today I wanted to give you a general intro, a general lecture on large language models, but also have a bit on healthcare and a few applications that we could do. If you have questions, you can interrupt me. That's fine. Or we can also reserve some time at the end for questions as well. Since you all are doing a stats and epidemiology, sorry, the masters, I feel like we could actually talk about some modeling and some math as well, but just slightly. One thing that is helpful to get the conversation started is remember on, or at least refresh our memories on what a model is. We could make it very, very simple in the sense that we could say that a model is a mathematical recipe that uses information or our features, our variables, to estimate or predict something of interest, which is our outcome, right? If you think about your epidemiological study, you would use like a logistic regression to using some demographic features, some clinical features to predict if the patient is the patient going to survive, what is the odds ratio of this patient having this condition, etc. And you could actually have a very simple model like this one, which it would be like a linear regression or something, where you are comparing your covariate with your outcomes, or here height, to predict weight. And you would have some sort of course, you would have your equation, which you're going to have your intercept, your weight or your coefficient for the first variable, and then some sort of model error. And depending on your R square, depending on your model fit, etc., you're going to get better or worse predictive outcomes, right? If you think about this in the realm of statistics, you would basically take the coefficients and use these coefficients to interpret the meaning, saying maybe the relationship between height and weight is that for every point, every centimeter that you get in height, on average, you're going to get 2 kilos. Maybe that's the interpretation you can get. But then when we talk about this in machine learning, what we are more interested in is actually predicting, can we use this model to predict on unseen patients or unseen data, and then essentially create these like predictive machines, predictive models to use them. And of course, you are interested in the error, how much error you're getting, right? And this example here, you would have like a least square error method where you try to minimize the error, for instance. Of course, this is all for a supervised approach. I see that you had a lecture from Virginia earlier. and she talked about unsupervised models. So the approach is a little bit different if you're talking about unsupervised models as well. If we go a little bit more into detail, like if we think about how the data is organized, how the model kind of works, you would have here in the left your patient information. So every row here, every line is a patient or a case, and every column is your variable, is your feature, is your predictor. We can use different terms for these. While the Y here is your outcome. Okay, so you have patient one, you have all of their features, you have patient two, all the way to patient N, and then you would have 500 patients, 1,000 patients. You get a picture. When we fit this using a logistic model, essentially we are trying to use the model for the model to learn what are the weights or what are the coefficients, what are the adjustments that we need to do in order to get a good prediction. So essentially what your machine learning model is trying to do is to learn how the variables correlate among each other, among themselves, and how does this correlate with this probability of the outcome. For a logistic model specifically, you are learning the coefficients here, which are going to get you like the log odds, for instance, the logged prediction, which is going to be a raw score. And you would apply this raw score to like a sigmoid function and then transform this into a probability. If you have done logistic before, you probably have the experience that the number that is generated, if you take your logistic model and predict on your same patients, you're going to get either a classification. So it's either going to be 1 and 0, depending on your outcome. So if you're talking about dying or surviving, you are going to get either the patient dies or the patient survives based on your model. But if you actually take the prediction instead of a classification, you get the probability, you get the value like a response prediction. You're going to get a probability of the patient having the outcome, and that's the number. That's the magic number I want to say. That is a result of your model interpreting the case for that patient specifically. So let's say we have, I'm seeing that there's probably more than 10 people. I can see more than 10 people in the classroom now. We could possibly get several ranges of these predictive probabilities. And depending on the predictive probabilities that each of you would get based on the model will tell you, will try to classify your outcome based on that probability. So by standard, what the logistic model does is that if it's more than 50%, the model says that you're going to have the outcome. If it's below the 50%, the model says that you're not going to get the outcome. All of that to say that in the end, you are learning these B values here, which are your coefficients, which are your weights. To get a raw score, you are applying some sort of function to transform that into a probability. And that probability is what is going to give you your result. Okay? This notion is important because then this is a very simple model, and we start to think about more complex models. In this example, we start talking about deep learning. So deep learning is also a form of machine learning, but the difference is that we have a model that is not straightforward. You don't have this relationship anymore where you have your data, you have some sort of transformation to get your raw score, and then you have your probability. That would be we would call this as like a single layer of prediction. But then when you start to talk about neural networks, which are not super new, they have been around like for more than 30 to 40 years, at least the technology, at least the theory behind this, is that with the neural networks, you start to stack these predictive models on top of each other, these predictive layers on top of each other, in a way that you are actually transforming your data every time in every layer. In that sense, you try to extract more information that would not be available at that standard format. To give you maybe a more structured example, you could think about this initial layer here, the base layer, which is connected to this Z layer as a logistic regression, because you're transforming your data, you are applying some sort of a sigmoid function here, and you're going to get some sort of a probability. Out of that probability, you apply another layer of logistic regression, and then another layer, and then another layer. And this is where we talk about deep models, because in each of these layers, you are transforming your prediction, you are transforming your data in order to try to extract most meaning possible. So in each of these layers, you're going to transform this data, and you're going to get a probability by the end. So the logic is quite similar. The difference is that you have several of these more simple models stacked on top of each other, and then you get this probability by the end. Okay. And with the deep learning process, we now talk about this machine optimization process, where you're going to repeat this process of fitting your data, seeing if your model did good or did not good, or if you need to improve your parameters. But in each of these cycles of optimization, you're going to also try to learn the weights or the coefficients that actually improve your model. So it's the same logic as the standard logistic model, but then you are doing this with many, many layers. So you need a lot of computational power, you'll need a lot of data, and you need probably a lot of time, and probably much more money in terms if you think about computational resources. If you run a logistic regression on your laptop, that is probably going to run in a few seconds, depending on your data, maybe like 1 minute or so. But then if you're talking about like a multi-layer perceptron, which is this example here, or even a big deep learning model, you're probably going to be, your laptop is not going to be enough to do that. And then if we take this example of the multi-layer perceptron to something that is more abstract and more like actually applicable to what folks are doing for the models out there, we can look at this example from a convolutional neural network. So this is a CNN. It's also a type of network, neural network. And a CNN is a very good architecture, a very good modeling approach for you to do image recognition. This is something that folks like 10 years ago, researchers were trying and saw that this actually worked much better than all of the other modeling approaches. And this works specifically for images. So if you're doing like, if you have you do your social media post, and then sometimes there's an option for you to add a subtitle or a legend or something. You sometimes get a sense of the social media says, in this picture, you see a cat, a dog, and a person posing for the photo. That process of recognizing the image and extracting meaning is probably being done by a convolutional neural network in the background. And although this is much more complex than the images that I was showing you just now, the logic behind this is the same. We don't need to learn all of the math now. It's just to think about how this works. In each of these layers, you're going to get some sort of data transformation. So instead of going from your data to prediction to probability, as you would do with a logistic regression, you go from your data, you transform your data a bunch of more times, and eventually you're going to get a probability. So in each of these layers, you are transforming, you are reducing, you are expanding, you are multiplying, dividing, etc. your data, and then by the end, you're going to get a probability. And this probability, differently from the logistic, which is going to be just a 1 and 0, like a probability of having or not having the outcome, this is a probability for all possible outcomes. So let's say we have a database with 1,000 types of animals, like pictures from 1,000 different animals, species. You're going to get a probability for all of them. So maybe since this is an image from a cat, probably the probability of this being a cat is going to be like 90%, while the probability of this being a alligator is going to be 10%, or a horse is going to be 5%, etc., etc., etc. That is the difference. And you repeat this cycle many, many times. So n cycles of optimization, you're going to learn the weights. So every time your model is attempting to predict your outcome, the model is learning coefficients, the model is learning weights that is going to improve your prediction performance, and eventually you get something that works. Okay. And that's a general process. All of that because I wanted them to get into large language models. So how are they different? How are they similar to this notion? The thought process is quite similar. This is a deep learning model, like large language models are deep learning models by definition, because we have a lot of layers, we have a lot of processing. But the thing that I want you to think about is that for all of these other models, like for the logistic regression, you're predicting your binary outcome. For your multi-layer perceptron, you can have multi-class outcomes. For an image, you can have thousands and thousands of possible outcomes, and you're going to get their probability. But with a large language model, you are trying to train the model to predict the next word in a sentence. Okay? So think about this problem where as you are typing to ChatGPT, what ChatGPT is doing is that it's not like a human that thinks about the whole sentence first, doesn't think about the whole context first. What it does is that based on your question, based on your prompt, it's gonna get the probability of what is the best word to be responded, to be given to you. So in this example that I have, this very simple example, the model calculated that the best word to have here is I. And then the second best word based on the first word and based on your prompt is want, and then to, and then eat, and then candy. So for each of these words, these tiny words, the model is doing calculations to say, well, based on what I learned on my training data, what is the most likely word that is going to come after this word that I just said? It is kind of like an abstract way of thinking, because when we think about how we humans learn language and how we process things, seems to be, much more intuitive. Like you think about the whole concept first, etc. But this model is actually generating text. It is not thinking, it's not remembering, it is generating. And this notion that GPT or any of these models, sorry, they are generating, actually makes you think about how dangerous this could be, because they are going to give you an answer regardless. They're going to tell you something regardless if it's correct or not. They're just going to generate text, right? And for each sentence, each phrase, each word, they're calculating the probability of using that word or the other word. Okay. And it's a probabilistic process, so there's actually a lot of room for error here. And it kind of works, and it works great because first, the technology is great, like the modeling, the math behind it is awesome. Then the amount of data that is used to train these models is like huge. They like essentially they used all of the content available in the internet and maybe more. Um, and they have a lot of computational power, like a lot of money to invest in this, and eventually it just works. If you would try to do this with your, let's say, like you have a book that you're reading on your laptop or something, and you would try to train a large language model with just this book, it would be terrible, because the examples are like too small. You only have a few words, a few hundred pages. That is not enough. You need much, 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 much more data to make this work. And of course, you probably have seen some of these company logos, like the most recognizable here probably is OpenAI. That ChatGPT is probably the most famous here because how big it got. But you have a lot of competition. You have a lot of other companies trying to do their thing. And you even have folks that develop the models and make their codes available, make the model open source. So you could use it on your institution, your workflow without paying. But then how do the large language models learn? Like how can they actually understand like a book? How can understand a social media post? How can understand a question? It's as I was saying, it's similar to a deep learning architecture. We need a lot of data. We need to learn weights. That is going to improve our accuracy. And we need to repeat this process a lot of times. In detail, we have here the uniqueness of the transformer infrastructure, and I could even say maybe instead of infrastructure, I could say architecture for the model itself, and attention, which I'm going to get into. And with that, just to give an example, why GPT is called GPT is because it's a generalized pre-trained transformer. And transformer here, it's because this is a new model architecture. Like I showed you, there's the architecture for the multi-layer perceptron, there's the architecture for the convolutional neural network, and the LLM uses something new. Okay. But before we get into that, let's talk about attention. Maybe you've heard this phrase elsewhere. Maybe you had the chance to see some other lecture that talked about attention is all you need. This is a very important paper, like a groundbreaking paper that was published in 2017 by a few authors at Google. And that's where they proposed this transformer architecture. And what they call attention is actually a mathematical representation of attention, where you try to make the model consider things that are closer to each other. Like if you have a sentence, if you have a few words, you're going to probably have the model consider that candy and eat are much more similar or much more connected to their meaning than candy and I, right? And with that, the model kind of learns what is important because of their proximity, because of their weights, etc., etc. To give you a very, very silly example, let's try to transform this modeling approach and use a person here. I'm using myself just for the sake of ethical reasons. Didn't want to put anyone else in spot. But imagine if you would have a person and you would have a set of features for this person, right? Each of these bars, they represent their features, like their characteristics, their demographics, their hobbies, what they like, what they don't like. And you would get some sort of a score for these features. You could talk about this like a coefficient. You could get some sort of weight to how much this feature is important to represent this person. In my case, you have here, my name is João. I'm a Brazilian, I'm an art coder, but you could have many more, right? To describe a person as you would for all persons. My representation looks like that, but if you take another person, like your very own Professor João Ricardo, we could have a similar representation based on similarities and differences, right? So in this example, we have a few similarities in the sense that we are both named João, like our first name is João. We are both Brazilians, and we are both art coders, right? So we can see how the features here, the bars are exactly the same for these features. But then when we look about what is different among us, we could also think we can also think on how our backgrounds are different. Like João Ricardo is a psychologist by training. He has experience in implementation science. So our features are not the same, right? We have different weights different features, different levels of these features, based on how similar or how different we are. If we actually take this and think about like a scenario, like let's put ourselves, like João and I, in a scenario. So this is a picture from the first KCMC symposium. I think it was back in 2023, if I'm correct. Both João and I are in this picture. You can see that João Ricardo is here in the front, and I am there in the back. You can use the proximity of these people, of like people around us, to try to adjust our features. Because maybe being a psychologist is not as important for João Ricardo now, because he's surrounded by people that maybe are all medical doctors, maybe are all epidemiologists, or no one is a psychologist here. Maybe that's the case, right? That's not what I'm saying, but just an example. The same way, maybe for me, being a Brazilian is not something that is very meaningful, because here we are surrounded with people from all around the world, but more specifically, a lot of people from Tanzania. Maybe that's a feature that is not important to describe myself, because I am different from other people, and maybe that's not important. So what I'm trying to say is that we can adjust our weights, our coefficients, based on where we are, like based on who is among us. So we can take that every single person here has their own set of features. You could have, like, I see the Catherine Staten is here. She has her own set of features. We have Ashley, one of our colleagues. We have Prof. Landina. They all have their own features, but what we want to do is consider how similar we are among ourselves and how different we are, to adjust these features, to give them new scores, to give them new weights, in order for the model to learn how to understand people, how to understand data. In this example, we are talking about people. And then eventually you're going to get updated weights based on proximity and similarity. Okay. And this is exactly the same for text. Every word, every sentence, every phrase has their own features. Maybe you could say something like have here. This word here is a verb, so it's going to have a feature that is related to verbs. Is a feature that is related to English. That kind of stuff. While the other words are going to have all other features. In this concept of attention, similar to the example I was showing you with people, we can use the proximity of these words and how often these words appear, right, close to themselves, or how if you take 1,000 books from your library, and you think and you kind of get a score of how close have is to shall or is to them in all of these books, you kind of get a sense of how important these words are together versus any other types of comparison. And that's the way the model learns language. It is by comparing the similarity, comparing the proximity actually of these words, how often they appear together in the training data, in a way that by default, by the end, after all of these optimization cycles, the model learns how to add the next word. So if we go back to the example on I want to eat candy that I was showing you, that's where that comes from. The model learned that those words have a relationship, because that's how you assemble a sentence in English. Like you have your pronoun, and then you have your verb, and then you have your preposition, and then you have your verb, and then you have your noun. Right? That's a way for you to assemble your sentence. And that's the same for Swahili. That is the same for Portuguese. That is the same for Italian. Whatever. Each of these languages, they have their different I want to say specificities, but when you have a lot of data available to train the models learn how the languages work. It is very different from you going to school and having your professor, your teacher telling you, well, the phrase that you just wrote is wrong because you should not have a verb and then the noun. You should have the noun and then the verb, etc. The model is not reasoning. The model is doing math. The model is looking at data, comparing the data that the how the data looks across all of this vast amount of data, and that's how the model learns. Okay. I wanted to stop here. I promise we're gonna go to a bit more of a fun part. Anyone has questions or wanted to go back to any of the concepts before? Um, Let me see if I can see. Don't see any hands, so I think we should be okay. Cool. All right. So let's talk about applications. Let's talk about applications in healthcare. Okay. So large language models are great. They have transformative potential in healthcare because they are really, really good at doing a lot of things. Because different from your logistic regression that we are using as an example, they are not trained to predict a single outcome. They're not trained only to predict mortality at KCMC emergency department. They are trained to predict the next word, and that applies to many areas of knowledge. Pretty much anywhere we use language, this could be applied. So the model becomes very, very good at interpreting language and responding to language. So it's kind of good with everything, right? Um, so we could have this as an assistant. So if you have watched, like those science fiction movies where the researcher or the lead actor, the hero talks to like artificial intelligence and says, "Hey, I want you to call someone for me." Or if you have used like Siri or Alexa or any of these voice assistants, or even something like from Google, like Hey Google or something on your phones. This is the idea where we could. Oh, yeah, I said Siri, so my cell phone responded. Sorry. um, you could have these models as your assistants. And in healthcare, there's a lot of room for improved processes with these assistants. For instance, we could have a model helping clinicians responding to patient messages. We could have a model helping doctors generate discharge documentation, like instructions for the patient when the patient gets home. And we could also have models helping with clinical decision support, which is like what people want, right? You think about an assistant that is going to help your nurse, your doctor, your primary care physician, etc., to think about what are the possible causes. But of course, there are situations where the generalist model is not really good, right? You don't want a model that is pretty good to take care of patients. You want a model that is perfect to take care of your patients. You don't want the model to make mistakes. So I found this paper. This is a systematic review published in early this year. It's on current applications and challenges in large language models for patient care. And they go on about a few of the attempts, the applications that are being done. Just to show an example from the final papers that they included on their review, here in the y-axis, we have the field of medicine that this has been used. So on their research, the field that is using LLMs the most is ophthalmology, then followed by gastroenterology, then head and neck surgery, etc. So it's vastly growing. This is only peer-reviewed articles. So if you are not familiar with the publications on computer science, it is not as common for them to go to peer-reviewed journals as we do in medicine. They have the peer review process, but that's usually done in conferences. So they submit their publications as their manuscripts as preprints. These preprints are then submitted to the conferences, and then through the conference, the work is judged and approved and published, etc. So this is on peer-reviewed process, like the standard medical journals. So probably there's a lot more that is not showcased here. One thing that we can look and think about in terms of limitations and application is that 94% of the applications here were done in English. So you can think about this in terms of limitations in applying these models elsewhere, because maybe these models are not as good for Swahili, they are not as good for Portuguese compared to what they are for English. So that's one thing to think about and to tackle this in the future. But then they have this really nice figure where they describe a few applications that have been done. So they ended up getting, in terms of like a medical question answering chatbots, which are like 84-ish on their total. But if we would classify these approaches, most of them were focused on the patient aspect, so interacting with the patient somehow, and the 25 of them were focused on caregivers specifically, so like 25 of them. But then you would have some approaches that were generating patient information, like medical text, summarization, or translation. You could get something like a simplified radiology report, patient education materials, patient-friendly medical responses, and so on and so forth. But if we think about the clinical care pathway, we have models being developed for prevention, for preclinical management, diagnosis, treatment, and prognosis. So we have all the way across the clinical care pipeline, I want to say. And this is really, I really want to say fun, in the sense that you can think about resolving or tackling these problems in each of these steps, and think about how you can, an assistant, like a large language model assistant or a machine, can help you do that. And I think that this is a good paper for us to reference in the future. But let's talk about a few concrete examples, right? So we talk about discharge notes. It is quite common, like if you are an AD physician, or if you are, someone in a very busy clinical schedule, that sometimes you spend more time talking to more and more patients, and you have less time to actually transcribe the notes, transcribe the case, generate like a report, so for documentation, or to give this to the patient later. This is a big problem in medicine overall. Like, there are studies on how even if you think in terms of profit for the hospital or etc., the times that the clinician is spending on documentation is a time that the clinician is not seeing a new patient. So this reduces the revenue in a sense, but also if you think about proper care, right? There are patients in the waiting room feeling pain that need to get care, and this clinician, this doctor, this nurse, etc., is stuck writing notes, is stuck writing reports, which takes away some of the care, right? So this paper is one example of this rationale, where they try to do compare discharge summaries from physicians and large language models. This is also published earlier this year. And in this approach, what they did is, I'm not showing the whole analysis here, but for specifically what they did here is that they had a group of physicians and a group, and then a large language model to generate the discharge notes for patients. And they have evaluated things like comprehensiveness, concision, coherence, global harmfulness, and global quality rating. And these ratings were done by other physicians, by other healthcare professionals. We actually had nurses, hospitalists, we had different levels, different professionals doing the rating. to see if the rating changed based on profession as well. But essentially, they would rate these summaries blindly. They didn't know if this was done by a large language model or by a physician or by a professional, sorry. And they would rate the response, the discharge note based on, is it good in terms of comprehensiveness from 1 to 5? Is it concise from 1 to 5, etc.? And what you can see is that there are a few fields where you don't have any difference at all. Like they did a comparison here on the mean and standard deviation, but in terms of coherence and global quality rating, that wasn't really a difference. So that's reassuring. But interestingly, for comprehensiveness, the physicians' responses were better. They were rated better with a significant p-value here, showing that overall people, like other healthcare professionals, preferred the discharge note generated by the a real human, right? On the other hand, when you look at concision, the large language model actually had a higher score. So that's interesting. So saying how this has a lot of potential to be implemented, right? I'm sure that you're probably thinking, well, I don't want a machine doing all the things for me. If I'm a patient, I don't want to get care by machine. But this could at least speed up the process where the machine generates a skeleton of a summary of a discharge note, and then the clinician can take over as well. And similarly, in the same paper, they also looked at the preference in terms of percentage for each of the professionals that were rating these. And if you actually compare the overall preference, people tended to choose the physician-generated summary, so the human-generated summary, while 36% of them preferred the large language model, but 16% of them had kind of like equal preference. So it's pretty close. So that's quite cool. I'm going to speed up a little bit. João, I think we have more like 15 minutes, 20 minutes. Is that right? Did you do you have more like
Yes.
15 to 20 minutes?
Yes, correct.
Okay, cool. Should be enough. And then for another application, this is a paper published in 2024 on using large language models for generating response to patient messages. And this is, sorry.
There's a question here. Hang on.
Okay.
Yeah. Find it. Yeah. So he's asking in the previous paper if the raters were aware of which documents were created by LLMs and which were created by physicians. No, it's blinded,
No,
right?
it's blinded. Yeah, that's a good question. They are blinded.
Sorry. Go to the next table, João, please. How they assessed equal preference.
Then after the blind evaluation was ready, they had the chance of looking at the two responses for the same patient, and they would choose each of them, like what response they preferred, but it still was blinded. There were people that chose the physician generated, people that chose the LLM generated, but then there were people that said that it's all the same for me. It's equal. Okay. Cool. Thank you for the question. Moving on, an example here now on patient messages, responding to patient messages. This is something that happens a lot, like patients get discharged. They want to know if they should take the medication after a few days or not. And this example is from 2024. Similarly, what they did is that they had the same sort of evaluation, but now they are patients rating the responses. So each line here, so it is a ChatGPT 4, 3.5, This is their own version of the model called Claire, and this is the provider response. And the patients we're going to rate if they preferred one answer over the other. And essentially, the blue lines are the agree or strongly agree, where they preferred more the one of them versus the other. The general picture here is that we also look at empathy, accuracy, responsiveness, and usefulness. And the overall the models seem to have a better rate of strongly agree for empathy, for accuracy, for responsiveness is kind of the same. You still have a lot of a good strongly agree for actual provider response. And then for usefulness, that's where we have the biggest difference, where the responses from the model were more useful for the patient. This is a perspective from the patient. In the similar scenario, this is all blinded. But then if you actually look at the actual answer, so like this is a snapshot comparing a response to a patient query. So this is the question. I could really use sleep aid. Recently, I've been having a night or two, sometimes four, where I just can't sleep, etc. This is the message that a patient sent for the clinician. This is the response that the clinician gave. So this is a very short response. I would suggest to try melatonin 6 to 9 milligrams at bedtime, etc. Thank you, Dr. Blah, blah, blah. This is the response that the GPT gave. It is a more thorough response. Is that I actually even cropped some of it. There was more text to that. So it's a more thorough response. It's a more detailed response. Maybe that's why the patient felt that this is better. But in terms of maybe clinical effectiveness, or maybe in terms of clinical meaning, both of them would be kind of correct. But the patient felt that this type of answer is better, is more helpful than this one here. Okay. All right.
So João, did the LLM response also gave the same accuracy at some point to use 6 to 9 milligrams of melatonin? Or was it a more generic response?
No, they solely focused on the patient perspective of it, like how useful that was versus and not on the clinical thing. No.
Yeah, no, my curiosity is, you said you cropped some of the answer. In the answer, does it at some point talk about the dosage of the sleep aid?
I don't think so, João.
Yeah. It makes
But
so much sense.
maybe that's one thing on how the patient feels like heard or
Yeah, no,
something.
that's what I'm saying. Like, the patient asks this question, like, I can't sleep. And then the physician says, take this pill, leave me alone. And then the chat, hey, come here. You know, this is so hard. Life is hard. Come here, let me give you
Yeah.
a hug. Maybe you could try exercise. But there's these sleep aids, but you know, there's things for you to do. And then they sleep well.
Yeah, therapy, etc. Yeah. It's probably a matter of acknowledgement and then feeling.
Exactly. I love it so much
Yeah,
fun.
yeah. Maybe it tells us more on the psychiatric and psychology support that people need, rather than the medical advice on like specific cases. But well. Okay, so we have a few. I don't think we have a lot of time, so I really wanted to focus on this one. Maybe we can skip the rest. But one thing that is really, really cool and is really, really impactful is to think about agents. Um, think about your large language model augmented with the ability to act and not just generate. So think about you going to your virtual assistant and saying, hey, I actually want you to call this person, and then based on their answer, send an email to my friend, and then put a reminder on my calendar for me to pick up something, like for me to not forget to do something. This is the difference from you going to the website and typing, hey, how can I fix my code, to actually telling the model to, hey, I want to do this analysis, figure it out. Go into your memory, go into your codes, figure out how to do this in R or in SAS or in Python and give me the results. It is a process where you can make the model reason, make decisions, and take actions in the real world outside of the model. So one example one challenging task that was pretty famous a few years ago is that the LLMs were pretty bad at math, like simple math. In this example, the user said like this simple equation like 241 minus 141 plus 1. And then the LLM gave an answer that this is 484. If you would count this, is actually 483, the right answer, but the models had a really hard time processing math. Because this is a limitation in the process, that the language of math is not really represented in the language of text, so it's really hard for them to learn. Now they are much better. An agent would actually do something totally different. An agent would actually go into the process and recognize the prompt by the user. They would they would recognize that the user asked for a mathematical expression or equation. And they are going to, instead of trying to come up with an answer, they are going to create a function in programming language, like in R, in Python. And they're going to run, so you can see here, this is a bit of code, like they're running calculate expression, and they are printing the result. And then you get the correct result. This works because the models are really good. They learned a lot of programming language on their training data. And then if you give them the ability to run these functions, they can actually get to very good results because the functions are standard and they work. Okay. A very good example of this as well would be that we could also have agents debating on the answer. In this example, you have a question. So how can I improve my time management skills? And you have an assistant, which is your large language model. You have your assistant 2, which is your other large language model. If you do the standard approach, maybe you're gonna get a response that is not as good because the model is just gonna think about one perspective. You can have these agents debating and reasoning. So you can have the first LLM saying option A, the second LLM saying option B, the third LLM saying option C, and they're going to debate among themselves to give you a better answer. This is also really cool because then it improves the accuracy of the response and reduces the errors as well. And an example that you can try if you have the access to GPT, I think they also make this available for free on the agent mode. If you set the GPT process for agents, I asked this question just yesterday. Get the temperature averages for the last 5 years in South America and generate a data report using Python. That's the only thing I said. The model then showed me that the model was going through Google and searching for South America average temperature 2020, 2021, 2022. And these are a few of the websites that the model found. With the results that the model found, the model then created like a virtual computer for them to run Python. Then after creating this, the model generated a plot for me. So you can discuss if this is a good plot or not, but it is a plot done in Python using matplotlib, which is a package that we use in Python. And then not only it generated the figure, but it gave me a PDF report on the methodology, the data sources, the results found, the visualization generated, all without me doing anything. Right? This is crazy. Like this is the potential for these things is phenomenal. Of course, you can talk about, well, we need to take care, we need to make sure that these sources are reliable. I agree. But the potential that this has is actually crazy. And then just to wrap up, I think that one thing that we should focus in this last few minutes is on retrieval augmented generation. And this touches on the concept that I kind of touched on before, that is your large language model is never gonna say, I don't know. The model is never gonna not give you an answer. The model is always gonna generate something. So this is me yesterday as well saying, give me a 3-sentence summary of how the phases of the moon can impact my machine learning results. To summarize, they can't, right? This is like total gibberish. Oops. Are you on again?
Yeah, sorry, my connection went off. Can you come back?
Sure. Are you seeing my screen?
I am seeing your screen. I think we were on the previous slide.
Yeah, okay. So yeah, so this was on the agent report, the possibilities, etc. Did you get to this?
Yes, you were explaining this part.
Yeah, so not only the agents performed all of it, but they also gave me an output. So you could think about fitting this into your workflow where the agent is going to look at the patient history. It's going to summarize the patient case. It's going to consider what type of clinical tests should be ordered, and they can give you a PDF, a report for you to then base your knowledge with your knowledge plus the report and think about possible strategies for your patient. Just an example. Finally, the thing that I wanted to focus by the end is on the retrieval augmented generation, which is the thing on your model is never going to say, I don't know. Your model is never going to tell you nothing. It's always going to give you a response because it's generating response, even when you ask silly things. Like I asked, give me a 3-sentence summary of how the phases of the moon can impact the machine learning results. They can't, right? That's not the case. But after a few iterations with ChatGPT, I kept saying, well, I have this data that tells me that the phases of the moon impacts the computer capacitors, etc. And that the model actually trusted me and gave me an answer saying, in the phases of the moon, influence computer capacitors, then they can introduce subtle fluctuations in how hardware process information, etc.
Sorry, João, you're not.
No problem. Do you wanna turn off the classroom phone so you can keep only a single connection?
I think I think my phone. First, somebody had called me, and like now it's over. So I
Is it
canceled
okay
the
now?
connection there. So I'm gonna take you. Let's hope.
Okay.
Carry
The
on.
example is we wanna improve the reliability of the model output. To do this, we can do something that is called retrieval augmented generation. So essentially, the concept is instead of the model just giving you a straight up answer based on the memory, based on the training material, you can actually drive the response considering some reference guides, so guidelines. So imagine at KCMC, you wanted to get a response if you should do a MRI, you should do a CT scan, sorry, for a patient or not. Well, instead of the model deciding by itself, you can attach, you can make available the TBI clinical practice guidelines from KCMC. You can also add the TBI guidelines from the European Association, from the African Association, from the World Health Organization, and then the model is going to look into those criteria, that reference material, in order to generate the response. The concept is exactly that. Like you have the question, you're going to have a retriever, so an agent retriever that I talked about now, that the retriever is going to go into your knowledge base, going to find pieces of that knowledge that those guidelines that make sense based on your question. then they're gonna augment your response, the model response. So the model was gonna respond maybe 2 sentences. Now, based on the relevant documents, they're gonna improve their response and only use that content, and then they're gonna generate the response. So, for instance, the response is now based on latest evidence. Over 60% of people diagnosed with the October 2024 flu are, et cetera, et cetera. And this 60% comes actually from a publication, comes from a guideline. So the model is actually using real knowledge to generate the response. Okay, this is really powerful. This is something that can augment your response. And I think I might have an example. No, I don't think. I think I can have a study case example here that we are trying to do with some projects at Duke, where we want to be able to help clinicians decide on what is the treatment for sickle cell disease patients. And we are trying to do something that uses the retrieval augmented generation. Here, this is actually the output already for the model. So we have a case where the patient information says that this patient has a genotype of HBSS, so it's sickle cell anemia. The question that the model tried to search on the guidelines was what are the current management guidelines for patients with sickle cell anemia? And then the answer that we got is that the current management guidelines for sickle cell anemia according to the clinical practice guidelines, focuses on evidence-based management of acute and chronic pain. That is pretty accurate, but maybe not really what we wanted, especially because then there is an answer on hematopoietic stem cell transplantation, which is not what we wanted. We wanted to talk about pain and how to manage patient pain specifically. But then in a separate example, the chief complaint for the patient coming to the hospital was that they had severe bilateral leg and lower back pain, consistent with vaso-occlusive crisis. And we used this patient information to search in the database what are the recommended management strategies for treating severe pain in patients experiencing vaso-occlusive crisis. The response that we got is that, well, it is recommended to rapidly initiate treatment with parenteral opioids, which is actually the type of drug that is used in this case, and that the dosage should be calculated based on the patient's current opioid use. So this is really accurate. If you go into the guideline from the American Heart Association, you're going to find that exact sentence. So that is actually quite good in terms of output, because we want to be as close to the data, to the evidence as possible. And then you can use this notion of combining large language model generating powers and evidence-based practice to many other fields, many other areas, many other questions. Okay, so these topics, both the agents and the RAG, are things that can actually improve the accuracy for healthcare applications, and I feel like those are like the main focus now, besides actually developing better accurate models, more accurate models. Okay. I'll send you the slides later, but just wanted to wrap up and open for questions, and we can cover this in another time if that's the case. Thank you, folks.
Thank you, João. Thank you very much. I think we're coming down to the time of the class. Do you have any questions? Okay. I think we're getting close to our capacity to keep listening.
Yeah, it is time for sure.
Yeah. This was great, João. Good overview. Thank you very much. And if there are questions that come out tomorrow, I'll make sure to post them for you. Okay.
Okay. Sounds good.
The lesson.
Thank you, folks.
Thanks, man.
Have a good one there.